Now, with that said, we can move on to looking at some span to depth ratios for beams. And unlike the column table, which had some confusing caveats off to the side here, this table is much more simple. We either have a cantilever condition or a simply supported condition, and we are either looking at a beam or a girder. And note that these given numbers here are all for wide flange steel beams. So now let's look at sizing some steel beams. And we're going to take the same 18 by 30 bay that we looked at earlier. And note that all of these connections will be simply supported connections. And so, looking back at our table, for the beam we will use a span to depth ratio of 24, and for the girder we will use a span to depth ratio of 20. So for the beam, if we rearrange this formula, we get that the depth should be equal to the length divided by 24. We convert the length to inches, we divide by 24, and we get 15 inches. And so looking back at our shapes database, the first member that has a depth greater than 15 inches is this W12 by 230. But note that this W12 by 230 is very, very, very heavy, 230 pounds per linear foot. And in fact, this section is likely used more commonly as a column section. If we scroll up further, we will likely be able to find a more economical section. Let's scroll all the way up to this W16. And here we can see that it has a depth of 15.7 inches, so greater than 15 inches, which is what we need. And it has a weight of only 26 pounds per foot. So let's choose this section instead. So that gives us W16 by 26 for our preliminary size for the beams. And for the girder, we will have D is equal to L over 20. 18 feet, convert to inches, divided by 20 is equal to 10.8 inches. Which means that we could use a W12 section. But note that when we are sizing girders, we typically don't want to go more than one size more shallow than the beams. And that's simply due to the connections. So in this case, if we have a beam that is deeper than the girder that it's framing into, we don't want to make this girder so shallow that it makes the connection between the beam and the girder too difficult. Instead, we want to look at a section that is at most one size difference away, one nominal size difference. So let's look at our shapes database and see if the W12 fits this criteria. And right away we can see that it does not. And that's because the next lowest shape size after a W16 are W14s. And after that comes the W12. And so for the girder, we should be looking at least a W14 shape. So let's pick this W14 by 22 for the girder. And again, these sizes are based simply on empirical data and experience. An actual structural engineer may choose to size up the girder for vibration control or deflection control or any other variety of criteria. But given this 18 by 30 bay, W16 beams and W14 girders is a decent place to start. And just for fun, before I close out this video, let's consider if the girders were framed in the long direction. And let's see what typical size we would end up with. So, if the girder were instead the 30-foot long member, we would have a D equal to 30 feet divided by 20, and we would end up with a depth of 18 inches, or W18. And so the overall structural depth of this typical bay would in fact be deeper, as I mentioned earlier, if we were to frame it the other direction. Now, to summarize everything that we've learned so far about structural steel, our first structural material, I've put together this structural material performance matrix. And we will be adding to this matrix as we move further along in the course. But for now, let's focus on steel. And you can see that essentially the way this matrix works, if we have this dark blue color, that means the material is well suited to accomplish the given design criteria without significant increase in material, cost, or labor required. If the cell is colored light blue, that means that the material can accomplish the given design criteria, but there would be some increase in material, cost, or labor required. And lastly, if we have this orange color in the cell, that means that the material is not well suited to accomplish the given design criteria, or that the increase in material, cost, or labor would be significant, and that there is an alternate material that is preferred for accomplishing that design criteria. And you can see here that steel does pretty well. Where it particularly shines are with large loads and long spans. Also with MEP integration, as we saw earlier. Steel is able to frame around openings in the slab very easily. Steel is also good for projects that may require future renovation. We can very easily size up steel members to be able to accommodate that additional load in the future. And the upsizing of the members won't really impact the schedule of the project very much. And that leads into the next point. As we mentioned earlier, steel can be erected very, very quickly. And typically, projects that are on a fast-track type of schedule will be steel projects. Typically. And lastly, as we mentioned before, steel is very good at minimizing the dead loads on the foundation because it has a very high strength to weight ratio, meaning that the overall building will be very light. Where steel falters, however, is with achieving very shallow structural depths. That isn't to say that you can't achieve structural depths that are shallow with steel. However, there is a more preferable material to accomplishing this particular design criteria. And if this design criteria happens to be your number one criteria when selecting a structural material, it would not be advisable to choose steel. Similarly with irregular building form, as we discussed earlier. Steel can accommodate some irregularities to the building form. However, there is a material that is much more suitable for accomplishing that criteria. And we will be talking about that specific material next week. But for now, that concludes our discussion on structural steel, our first structural material. So with that, good morning, good afternoon, and good night, and I'll see you next time.